Okay, good morning, everybody. So now today I start a series of lectures on optimal control systems described by partial differential equations, or so-called system with distributed parameters. Now, optimal control theory is a generalization of the classical calculus of variations, where you have minimization in the class of smooth functions. So when you want to minimize some quantity, some function or functional in the class of non-smooth functions, then methods of classical calculus of variation doesn't work. So in 20th century, optimal control theory made a huge progress, and in a sense, optimal control of systems described by ordinary differential equations has a complete theory, and Pontryagин's maximum principle one can consider this, this is the major result. Now, optimal control of systems described by partial differential equations is made also huge progress, and but it's not yet complete. So there is no general result like Pontryagин's maximum principle. Now, today I'm going to look to one particular problem of optimal control of the system described by second-order parabolic PDE. Now, let me write down the problem, and then I'll explain also its application. So assume that we are required to minimize the following functional, jv, okay, right here, integral 0 to L, have here u, x, the capital T, my dot v, minus some function fx squared dx. We'll assume that I'm required to minimize this functional. Now here's a v belongs to the control set. I'm going to minimize v in the control set. Let me describe the control set. V belongs to the set capital V. Okay. Now this is all pair functions. Let me call first element P and then F from the following spaces. So P belongs to the space of L2, 0 capital T. Okay. And the Lebesgue measurable function is square integrable in 0T. And F belongs to the space L2 in the Q. Okay. Now Q is a rectangle. Let me write down here what's a Q. Q will be the rectangle xt. Now x change from 0 to, let's say, some L, and T change from 0 to final moment capital T. So here in the set some other conditions. P is the values of P is between two values. Let's call them P min and P max. So in effect, Pt is a bounded measurable function. And now this is true for almost everywhere on 0T. Okay, this is one condition. And on F, I put also the condition that L2 norm of F. Now, I will define these norms also slightly later. So L2 norm of F is less than or equal to, let's say, some parameter R. So it's a ball in the space L2Q. Okay, so this is a control set. So you see, functions here are non-smooth functions. They don't have any regularity. In particular, piecewise continuous functions belong to this class, so even more general. Now you see when I minimize this functional j on v, but what is u? Because a given v from set v, I have to find this function u and then calculate this integral. Now here u, xt v, solves the following problem. The problem is partial differential equation solved the first initial boundary value problem for this PD. So problem looks as follows. Let me give here one. U satisfies the following equation. Du dt is a function of x and t and also depend on the control, okay, equal to a squared times d squared u dx squared. So second order parabolic PDE plus, you see this component f here, it sits here on the right-hand side, fxt. Okay, so you're required to solve this PDE. And one of the components of the control is the right-hand side here. Okay, the PD is solved in, well, let me write, I define already Q. So xt belongs to rectangle Q. Okay? Then we have here boundary conditions. Now, one boundary condition will be on the left boundary, derivative, x derivative is, let's take is equal to 0. Now I'll explain the physical meaning. This left end is insulated, no flux, okay? No flow from the left end. And on the right end, I have condition of the following nature. Dx is equal to, okay, here's some constant nu, positive constant times. And I have here p of t. That's exactly first component of this vector v, which is sitting here on the boundary condition. And then minus u L t. Okay, so this is should be satisfied in 0t. We can include that. And also initial condition for u, assume that u x 0 is equal to some given function, let's say phi of x, okay, which is everywhere. So here's a problem, is I'm trying to minimize this functional j in this control set, because given any control, this u solves this problem. Okay, okay. Here some data. So what is given here? First of all, this numbers, look, p mean, p max. These are the given numbers. Then we have here, let's say, constant nu, positive constant nu. T, capital T is given. Okay, and so function f is given. Okay, so assume that this function f belongs to space L2, 0L. Is again Lebesgue measurable function, square integrable. Okay, f is a given function. And what else? Phi is also a given function. Well, let's take also function phi belongs to L2, 0L. Okay, very general class. Okay, and so a is also a given constant. Okay, let's take a positive. So f and p are part of the control. Okay, so that's a problem. Now, where does this problem come from? Problem is from optimal control in thermophysics. Imagine that you have one-dimensional rod. Okay, so let me, here's a picture. So assume that this is x and t. So one-dimensional rod of length L. There's a heat conduction in this rod. Okay, so if you look to time interval 0t, okay, so that means rod at any moment t stands here. So we can we control this process. Okay, how we control this process? The heat conduction is going on, but there is several possible sources inside. So F characterizes density of the sources inside the rod. It's changed both in space and time. So I can control that. I can change density of the sources in the rod. Okay, and the P is characterizes temperature outside of the rod at the right end. Okay, so that means also I can play with it, increase or decrease, change the temperature outside of the rod near the right end. Okay, that means by changing this temperature here, the left end of the rod is insulated. There is no heat flow through the left end. Right end, I can play with this P, temperature outside, control. Okay, and so this is basically expresses. It's called the Robin boundary condition. So this is what I access. And also I can control density of the sources inside. Now I control this process in such a way that temperature is the final moment comes to desired form, Fx. So Fx is given. I want to control process through P and F in such a way that U temperature at the final moment comes close to this desired distribution. Okay? Now this is the optimal control problem, but equivalent problem arises also when you solve the inverse problem for PD. So this is basically variational formulation of the inverse problem for PD. Now the problem is mathematical. The following: imagine that you try to solve this partial differential equation. Well, if all the functions, in particular P and F, are given, this problem has a unique solution. Okay, but assume that you don't know F and P. So you have to solve the PD, but you don't know right-hand side. That means you don't know density of the sources. And also you don't know this boundary condition here, PT, function of the boundary condition. So of course then you can't solve the problem, you need additional condition. Additional condition comes in terms of the measurement. Imagine that you measure temperature also at the final moment. Okay, so that means this which is given through fx. And then having this measurement, you try to identify not only u, but also f and p. Okay, so that's the inverse problem, and the variational formulation of the inverse problem. So they're equivalent in a sense. All right. Okay, so now let's try to look to this problem. First of all, I have to clarify how I understand the solution of this problem. Okay, because, well, I have a partial differential equation. Control is given here. I have a partial differential equation which I solve with non-smooth data. F is the right-hand side, is very general L2 function, boundary condition. So obviously, classical solution of the PD problem doesn't exist. Okay, I have to understand solution in a weak sense, in a more generalized sense. So let me first of all identify the space which is where control belongs. So let me use this notation. I'm going to call space just H is a Hilbert space, will be L2 0T, where first component P belongs, and L2 Q. Okay, so this is a Hilbert space, and in this Hilbert space, we are going to define is basically dot product is defined as follows. If I take here, let's say 2 elements, say V1, V2, okay, so this is defined as integral from 0 to T, P1T times P2. First component you multiply and integrate in 0 to T, and then you take a double integral or integral in Q 0 to L. So you multiply also second component. So V1 is P1 F1, right? So it will be P F1 xt, and V2 is P2 F2, okay? dx dt. Okay. Now also you know that this is a Hilbert space, and in this Hilbert space, of course, we define also norm of the element as V2 1/2. Okay. Okay. Now, so assume that I have some control from this Hilbert space V, or belong to the set V. So how should I understand the solution of this partial differential equation? Okay. So for that, I'm going to give now a few definitions of Sobolev spaces, which I'm going to use. So let me briefly describe the spaces. Okay, so first space I will consider W2, 1, 0, Q. Okay, now this is a Hilbert space of